started. I'm sharing my screen. Those of you that might want to play with the Inspire might want to download this copy of the TNS file that we're going to look at. I put this in the chat. I will put it in the chat again. You don't need it, so don't worry about it. But if you do want to, feel free to go and do that. And I'm going to go in full screen mode. I'm Gail Burrill. I'm here from Michigan State University, the Program of Mathematics Education. I'm going to turn this over to Pip Arnold, who is the organizer, and she can introduce our colleagues here. Pip.
Thank you, Gail. And it gives me great pleasure to welcome everyone here today. Now, today might be Monday and today might be Tuesday. So I'm in Tuesday and it's Tuesday morning, and Gail's in Monday and it's Monday afternoon. And I know you're all somewhere in between and around that. So we just are so excited that you're here with us. And I would like to also just acknowledge the work that Gail and Monica and Alex have done to support the session getting underway. So I'm going to introduce those people. So Gail Burrill is at Michigan State University in the US, and Gail is our main presenter for today. But part of what we're doing today is we're going to do some workshopping with you using two different software tools and doing the two tools in English and in Spanish. So I'd like to welcome Alex from Texas State University and Monica Casillas from the University of California, Los Angeles, who are going to be our Spanish experts in the two software, and then myself, Pip Arnold. I'm based in New Zealand and I'm going to be doing the other English session in the breakout. So thank you again to our presenters, and thank you again to you all tuning up. And I'm now going to hand back to Gail, who's going to take us through the session with some help from her friends.
Okay, great. Thanks. Okay. So as we all know in our living, the pandemic has impacted us in a variety of ways. And interestingly enough, we probably never would have thought to do this workshop if we hadn't all been forced to go to Zoom and realize that it was possible. And so here we can have 50 people from across the world coming together to talk. I guess that's one of the not very many good benefits, but that is a benefit that's come from the consequences of COVID. But we want to use this opportunity to investigate the spread of a disease. And basically, we're going to work through different levels of the simulation, and kind of all together, we'll work through the first two levels. Then we're going to break up into 4 different breakout rooms. You can choose which breakout room you want to go to. We'll troubleshoot what you might not have understood from the first part. And then we will look at using the tools, the Inspire and the Code app, we will look in detail at a more advanced simulation, come back together, share some ideas, and talk a little bit about the theoretical approach. So why simulation? So basically, those of us that kind of engage in a data-driven statistical perspective really feel that simulation can help build understanding of statistical concepts. And it has lots of benefits, but for our particular purpose, it illustrates the variability inherent in analyzing information that's collected and disseminated. Too often, in relation to the pandemic, one vaccine test shows that it got a 75% efficacy, and then a week later you read, well, another test showed that it had an 80% efficacy. Well, people don't often understand what efficacy means, but they're very concerned because they're getting 2 different answers. Once it's 75%, once it's 80%, these people don't know what they're doing. That's an easy assumption to make, and one that we want to head off, because variability is inherent in how this disease is spreading. It's inherent in everything. And so we want to look at that and make that very visible for students. And there's some design principles that went into how we're thinking about this activity, along with some others that I've been working on. And by the way, I should give credit to Curtis Brown, who works with me from Texas Instruments, but also to the mathematician behind a lot of our work. It is Tom Dick from Oregon State University. And so our kind of way we believe things should unfold is informal before formal. And this is supported by the research that talks about how people learn. We also believe that delayed definitions, this is contrary to the way I used to teach. I would start by defining everything. And I have learned over the years that it's much better for students to engage in something and realize that a definition would be nice after they have worked with it. Rather than giving students a black box, we very much design these activities to be scaffolded so that students can make connections and keep that conceptual development growing as the ideas become a little more sophisticated. We reason a lot from sampling distributions and visualizations, which is not atypical for those of us in the statistics community. And we really think that at the end, there should be some kind of wrapping up or communicating about what went on or application of the idea. So these are our kind of foundational principles. So we're going to try something. I have done this in person and it works in person very well. But hopefully it's going to work in our Zoom meeting in the same way. So we are going to assume that there is a disease that has a transmission number or reproduction number of 2. That means that every person that gets the disease transmits it to 2 other people. We are going to assume that the days contagious is only 1. So we're keeping this pretty simple to begin with. And then we're going to suppose that 10% of our initial population is immune. They could be immune because they were vaccinated, or they could be immune because they already had the disease. So we're making some pretty simple assumptions here to get going. And we have 2 overarching questions we care about. How long before the epidemic ends? And what proportion of the population will not contact the disease before the end of the epidemic? So those are our 2 big questions. And so we are going to do a hands-on simulation that we hope will work. We have given people the numbers. We have given 20 people. That's our class, our population, numbers from 1 to 20. So they have changed their name from Asia to number 1. And we are going to have the numbers, those people with the names now 1 to 20, use the hands up symbol. And so they're going to raise their hand. Okay, so you're going to have lots of people raising their hand, 20 people. And then, because 20% of the population has the pandemic, is immune, they are going to lower their hands. So in order to make this work, I'm going to ask that the 20 people numbered 1 to 20 keep their images visible, their faces visible. And the others of you hide your picture so that when you're looking, and I'm going to actually get out of my PowerPoint right now. When you're looking at the screen, and I'm going to stop sharing, and you're going to have to just listen to my words. When you're looking at the screen, you're going to see only the faces of the people who have a number. Does that make sense? So we're looking at our class, and you see their raised hands. So number 7, we need you to raise your hand, okay? So we should have 20 people raising their hand.
Sorry, I'm looking for my hand.
Raising the hand symbol is under reactions. Find it?
There we go.
Okay. Everybody organized now? So we're looking at the faces. So number 9, we'd like to see your face. Number 7, hopefully we can see your face. And number 4, we'd like to see your face. And just for the time being, like Teresita, we love you, but we don't want to see your face right now. You're going to be in the back of the theater. So we're looking at the people whose hands are raised. And those are our 20 people that we care about right now.
So number 11, 12, and 17, we still need you to raise your hands, please. And if you can put your videos on, that would be great. But if you can't, that's fine as well. So 11, 12, and 11 and 12 still to raise their hands. And 17?
We got 11. Are we good?
We're getting close.
You can find the place to raise your hand under reactions. On my computer, it's across the bottom. And there's a little option that says raise hand, and you just click that option.
Okay.
Are we good?
I think we will have to run with what we've got.
Okay. So I want persons. Okay, so this will work. What numbers are we missing? Pip?
Oh, they're not in order.
That's okay.
It's hard to tell.
You just told me which they were, 11 and 17.
It looks like 11's missing. 12 and 17 haven't got their hands raised yet. And we look like we've lost 2 numbers.
All right. So let's have 11 and 17. They are our immune people. They have, for whatever reason, contacted the disease. They're not going to get it again. Okay? So they are lowering their hands, which is good because I never raised it, maybe. And I'm going to go and I'm going to generate a random number. And I'm going to just generate a random number from, let's say 1 to 20. This is a little hard. Okay. And I got number 15. Okay. So person 15, and Pip, you're keeping track of this, I hope. Yep. Person 15 lowers your hand. So person 15, go back to the reaction button and lower your hand. That person is our first infected person. And that person, person 15, is going to communicate the disease to 2 other people. So I'm going to generate 2 more random numbers. I got 1 and 19. So person 1 lowers your hand, and person 19 lowers your hand. Okay. In my class, they sit down. So the people are all standing in the front of the room, and as they get the disease, they then sit down. All right. So now we have 3 infected people and 2 immune people. The person 1 and 19 give the disease to 2 other people each. So I need 4 more people who are going to contact the disease. So I have person 12 lowers their hand. Person 11 lowers their hand. Excuse me. Person 15.
Already down.
And person 9.
15 is already down. So it's
Okay.
12 and 9 are the new people.
So 12 and 9 are the new people. So I can't generate only 4 more random numbers this time because there's only 2 new people who are going to infect 2 new people. So you have to have a really careful scheme of how you're counting and keeping track of things. Pip, do you want to share your screen about how you're keeping track? Is it in good enough shape to share that?
Yes, here we go. So the last round, these were the numbers that were called here. And I've recorded the ones that were newly infected because 11 and 15 were already in my list up here. And so now I'm just copying those ones down, ready for the next round. So I'll stop sharing if you want to do another round.
Okay, we're ready. I will generate some more random numbers. And this time I just generate 4 again. I got 12, 17, 15, and 3.
So 3 is the only new one.
All right. So now I only generate 2 random numbers. 3 puts their hands down. I got 1 and 5.
5's new.
I generate 2 more random numbers. 8 and 17.
8's new.
2 more. 17 and 17.
Okay, we're done.
All right. So now I need to know how many people still have their hands raised out of my 20. It looks to me like, Pippa, are we right? We have 13, 18, 14, 6, 20, 10, 2, and 7.
Yeah. I think we should have one more, but that might have just been we were missing.
And
we
4.
got 18 there and 4. Yeah.
Okay.
Okay, that's good.
That's good. All right. So we basically have 1, 2, 3, 4, 5, 6, 7, 8, 9 people who were susceptible but did not get the disease. So these 9 people, okay, this is going to give us this idea called herd immunity. Out of our 20 people, 11 people contracted the disease or were immune. So that 11 people out of our 20, or 55%, is the herd immunity threshold. So 55% of our population either started immune or got the disease. 45% of the population was not infected, did not get the disease. Does that make sense? Anybody have any questions about that? Thank you to our class. And essentially, yes.
Gail, the question is, it depends on how many rounds you're doing, right? The numbers that you're getting.
Yes. And so Pip can tell us, because she was keeping careful track, how many days did the disease last?
So there's our record of what we've done today. So it lasted for 6 days.
So we know the answer to the 2 questions. It lasted 6 days, and 55% of the people were either immune or got the disease. So
and Gail popped up how we did in our practice. So when we were practicing last week, we took 9 days to get to the same place, and we had 18 people were infected. So different. That's just showing how it is. Our one today, 6 days, and 10 people were immune. So sorry, I'll stop sharing there just to give you to show how it's very different each time you do it.
And that's that variability that I was talking about. So now feel free, 1 through 20, you can go back to your original names. You don't have to stay 1 through 20, and everybody can share their picture or not, depending on whether they're feeling comfortable to do that. And I'm going to look at the next level of how we might do this simulation. So I'm going to go back to my PowerPoint. Actually, I'm not. Just quickly back to my PowerPoint here, and I won't even go to the PowerPoint mode. I'm just going to do what we did, but I'm going to do it on technology. And I'm going to create a population of 100 people. So I'm keeping the same transmission number. I'm keeping the same days contagious. I'm keeping the same percent immune. And I'm changing it from just 20 to 100. Okay, so I'm still not going to thousands. I'm just kind of gradually getting there. And I'm going to do this by creating a scatter plot to represent my population of 100 people. And I'm going to create the scatter plot by generating random integers, 100 of them from 1 to 50. So I'm going to generate 100 random integers. So there's 100 little dots, and the horizontal and vertical axis goes from 1 to 50. And I can see my population. And then I'm going to copy the first 10%, the first 10 numbers, ordered pairs, and put them in the immune category. So that's my blue guys. So that's what I'm going to do. And essentially, the thing to remember here is that every dot comes from a row. So just like Aisha was number 1, instead of Aisha for our simulation, now number 1 represents the person in position 4824. So who's ever in 4824, somewhere around in here, is that person 1. So their name is this ordered pair under that row number. Okay, so I'm going to go back to my software here, and I'm going to go to the intro to the workshop. So this is what I'm going to do. The idea actually came from Wikipedia, where this is how they were explaining what happened. They used this kind of diagram. And I have the same conditions. I have generated on a page. This is a calculator page. I've created my 2 populations, like I said I would do. And now what I want to do is I type in pop_y, pop_x, and that gives me my ordered pairs. I copy and paste. And these directions I can send to you, or they are also on the TI website. So if you really want to use those directions. Mark has a raised hand. Mark, did you have a question? Or was
Sorry, no, I don't. I'm just following along. I'll sit down.
Oh, okay. Thank you. All right. So I've got my scatter plot set up, but now I need to get a picture of it. So in order to get a picture of my scatter plot, depending upon the software that you're using, I have to set up the window. And so my window settings I've already done, but they're set up to accommodate the numbers from 1 to 50 on the X and 1 to 50 on the Y, with a little bit more room on the Y so I can put some labels down there. Then I need to set up my graph. So I'm going to look at my view, and I really want it to be, I want to be able to see the grid, and I want a dot grid. So now I've got my dots. So these are my dots, my people, potential people, and I'm going to actually put my people on my grid. And so I need to go to scatterplot on this software, and I need to load in my X coordinate, which would be pop_x and pop_y. underscore y. And there is my population. Okay, that's my original population. So now I want to put my immune people in there. So I go back to my scatter plot again. And now I want to, and I can actually get these off the variable list. I want to put in immune X and I want to put in immune Y. I can either type the names in, depends on your software to do scatter plots. And now I have my people who are immune, which is exactly, this is the 20 of you that were standing and then the 2 people who sat down. That's exactly this situation. Okay. And now what I want to do is I want to go generate a random number. So I'm going to generate, let me get rid of that one there. I'm going to generate a random number from 11 to 100 because I'm going to get a newly infected person who's going to come into this community. And that newly infected person is not going to be 1 to 10. It's going to start at 11. All right. Person 34. Now let's remember what that means. Person 34 is the person in row 34. The arrow all the way down. I don't have to, but I found that people need to actually visualize that. Person 34 has got coordinates 49 and 15. Okay, so that's my first newly infected person. So I'm going to go back up to the top up here. I'm going to arrow over here. And I don't know what that's doing there. Let me get rid of that. I'm going to label this infect underscore X. And I'm going to label this infect underscore Y. And this was person 34. So I'm going to go equals 34. Sorry about that. A 34. And I'm going to use the spreadsheet functionality. It's just like Excel here. And it's calling up the X coordinate of the person that was in row 34. And I'm going to go equals B 34. And so I reproduce those coordinates. So now I need to say, well, what's going to happen here? I'm going to go back and I'm going to add in my infected people. So I can get that by picking up my infected X, by picking up my infected Y, and you can barely see it on my screen, but there's one little guy there, the infected X, infected Y, and he's way over in the corner. So that's the newly infected person that's entered into the community. Okay. All right. So what comes next? Well, that infected person, infected, I'm going to type a new math box here. That infected person, I'm going to get a rand int. I now can go from 1 to 100 random integers, but I have to do 2 of them because number 34 infected 2 people. So I have 44 and 78. So this is kind of tedious, but I need a 44, oops, forgot the equals a 44 and B 44. Oops. Yeah. And what was the other one? Does anybody remember? 78. Let's assume it was. I forgot the equal sign again. When I do this, I have discovered that it almost takes 3 kids to work together in order to make this happen. So it gets kind of difficult because you have to concentrate really hard on what you're doing and keeping track of everything. So I have somebody generate the random numbers, somebody else record which ones were infected, and the third one is keeping track of which ones we've already used because we can't use the same random number over again. So now there are 3 dots that are black on my screen. One there, and one there. Okay. So I continue this process, and let me just see. This is what it looked like. Pip, do you want to explain this?
Yeah, so that's my, when I started following it through to do it manually, pretty similar to what we did in the Google Doc that we shared before. But I started by writing down all the things that I had to think about, which you can see at the top. And then I set up my model that I wanted to work with that worked for me. And then so it's basically this same as what we did before manually. With the people's hands up and hands down. And then I started the bits that are sort of in the square brackets is when I started to match up with some of the things that we're doing now with the technology. So understanding, that the population size was the number of people, and, the duration was the length of time contagious. So that was what I was doing in my head, was doing it slowly so I could connect what I did by hand to what I was going to do with the technology.
Great, thank you. And so we continue that process of generating random numbers just like we did before. So 44 and 78, each infect 2 new people. So now I get 4, and Pip or someone is keeping careful track as we go through these. You can actually, you can fancy up this by collecting the numbers and displaying them on the screen so that you can look at them. I just tried to keep this pretty simple. But you continue that process, and I actually went ahead and finished it off for a set. And so I've done that until I reached the place where I generated these random numbers, 6 of them, and every one of the 6 had already been infected. So I had reached the place where I had herd immunity. The disease was not spreading any longer. And this is what that scatter plot looked like. So the disease was not spreading any longer. The gray in this one was the initial population. So the gray were the 100 people. The immune, the original 10% immune, are the little pink people. And the people that got infected from this newly infected person are the people in black. If you count the little gray guys, you will find out that 30 of them, of those who were susceptible, never contacted the disease. So that means my herd immunity threshold is 70%. So I have a 70% herd immunity threshold. Okay, so I'm going to go back to I can do one more thing here. You can also record all of the data, and you can make some pretty looking graphs. So those of you that like your kids to think about the mathematics, you might describe this curve, these 2 curves, and think about how they're related. One, the gray is the number of susceptible. The pink is the total number infected. And you can figure out where to read the herd immunity threshold off of the graph and things like that. So I'm going to go back to my PowerPoint and kind of wrap it up. And so we can get into breakout rooms. So this is what we did. And we kept generating the number of newly infected people randomly. And we got our herd immunity threshold. And in this particular example, it took 9 days. So our disease took 9 days before it died out. And 30 of the original 100 were not affected by the disease. So, like I said, we want to pay attention to the variability. So I collected from my little groups of students their herd immunity threshold and created a sampling distribution. So the sampling distribution looked like this. And obviously, different classes are going to have different sampling distributions, depending upon where your people are in terms of their statistical background or where you're trying to go. If you are a teacher and you are working with middle school students who don't even know about standard deviation, you can just talk about, well, it looks like the herd immunity threshold for those conditions is between 74 and 80%. But you could also do a confidence interval. There's lots of things that you could talk about. You could do some hypothesis testing. So you could actually, and here again, this is a middle school place where people could talk about, well, the median number of days this disease lasted, this epidemic lasted, was 12. But most of the time it was only 10. One time it went all the way to 17. Should I maybe look at the mean number of days? So there's statistical questions that you can look at from a very elementary level, as well as get a little more sophisticated with them. So we're going to actually now go into our breakout rooms, and some of you are going to go to a simulation. I'm thinking about CODAP in Spanish and in English. And some of you are going to do, and basically both of these simulations, some of you are going to choose to go to Inspire. Both of them are going to allow us to play with the parameters. So our parameters were transmission rate of 2 and days contagious of 1. And our population was either 20 and then it was 100. And so when we go to the simulations now that are the next level up in this scaffolding process, we can change those transmission numbers and we can change the days contagious. And we will do that by using different, actually both the software packages use sliders in order to create the graphs and look at it for students to think about. So I'm going to, Monica actually is going to put us into your breakout rooms, and Alex is going to do the Inspire in Spanish. I will do the Inspire in English. Monica is going to do the CODAP in Spanish, and Pip is going to do CODAP in English. And so, Monica, are you ready? And we are going to be in our breakout rooms for 35 minutes. Oh, and before we do that, does anybody have any questions that I noticed there's something in the chat. You can ask questions when you get in the smaller room in the chat, but you actually could ask one now if you want to, or you could just wait and ask one of us. Okay, Saleha, you have a question?
Yeah, I just wondered, do we have the option which one we can go to? The
Yes.
breakout room?
Yes, you do. Monica has set it up so that she has created 4 breakout rooms, and you will go and she will tell you how to do that. Right, Monica?
Yes. So right now, when I open the rooms, you'll have the option of hovering over the room that you want to join, and you actually could pop in and out of different rooms. Like you could go into the Inspire for a little bit and see what's happening. You could pop back out under the CODAP, but we probably don't recommend that because, you know, if you go in halfway, you'll probably be lost. So, but yes, you have the option. Just hover over and put join. And I'll wait out here until everybody's joined a room, just so, you know, no one's left behind. Here we go.
Do I have to stop sharing?
You don't have to, but
Okay.
you can.
All right. And they know which breakout rooms are English, Spanish.
Yes, if you look, you know, you can see the 4 that are available, Gail.
Okay.
Like I said, I'll wait out here in case someone's having issues and I can assign them to a room.
Okay, Monica, how do I go to a breakout room?
Okay, Gail. So you need to go to Inspire English. So click on the breakout rooms, go find Inspire English, and then there's 3 people there already. So just hover over the number 3 and then you'll see a join.
Inspire English.
Inspire English.
All right, I see it.
Okay.
Hover over and it says join. And I joined.
And you join. So again, I'll wait out here until everybody's, just in case anyone has issues. And then I'll go and.
So Becky Byer, I didn't even know that was you behind that mask.
Yeah, I'm still at school. But I was really excited, though. In between, I had to shut my camera off and go to a different room that wasn't being used during a passing period. So you've traveled around my building a little bit today.
So I know everybody. So Becky, why don't you introduce yourself to the other guys in here?
I'm Becky Byer. I teach computer science and statistics at Casper, Wyoming.
Leandro?
I didn't listen to what Beck said. She's from where?
From Casper, Wyoming.
Okay.
I teach computer science and statistics.
Okay. I'm Leandro. I'm from Brazil. I'm a mathematics teacher. Now I'm doing research at the university about education, maths education.
Lee?
I'm Lee Kuchera. I did AP statistics at the high school level for about 15 years. And now I'm at the University of California, Irvine, teaching the equivalent course.
So Lee, I don't know if Leandro knows what AP statistics is. He's from Brazil, right?
It's an internet, it's a worldwide program.
No offense. Okay.
I train teachers in Shanghai, Central America, all over the world.
What's the name of the program?
Advanced Placement, College Board.
Okay.
And I teach statistics within it and train statistics teachers.
Anna?
Kia ora, I'm Anna. I'm from New Zealand. I teach statistics and data science at the University of Auckland.
Kim?
Hello, I teach geometry and AP statistics in an online high school. So I love the hands and the pictures. It was just a powerful visual. Thank you.
And Lisa?
Yeah, Lisa's in and out of class. She sent us a chat. I bet you she's in the middle of dealing with children right now.
Oh, okay. So she's coming in and out. And Zula Kaha, who just joined us. You want to tell us who you are and where you're from, Zula? Can unmute yourself. Okay, so if you need help, let us know. You can type something in the chat, and we can try to figure out how to help. I'm going to share my screen and keep us moving. Does anybody have any questions that they would like us to look at or answer before we get into the next level? Any questions? Leandro, did I talk too fast? There's something you didn't understand?
Yes, you are not talking too fast, but the problem is with my earrings. Sometimes I lost some phrase, but I can keep it continuous understanding you.
Okay.
And I'm curious how detailed the instructions are on the TI website and what's it under? Where do we find them?
Mathematical modeling.
Okay.
And this is the simulation under mathematical modeling. I'll actually show the screenshot later on for that.
Okay.
Other questions?
Well, is it is it just instructions, or is it one that's already set up?
It's a complete activity that describes and shows screenshots from what I just did for the 84 and the Inspire. So you can do all this stuff on the 84 as well. And so Becky, the next piece is the coding piece. So Tom did the coding piece, but it's all done. So anyway, so let's look at this. Then you can raise some more questions. Okay, so this is the TI Inspire file that's available on the website, and you can click and download it. This is for Inspire. If you have access to a TI 84, you can download that, and it'll play on the handheld as well as in the software or the software emulator. So you can, if you have, like in my college work, my students all have computers, so they use the software. And because I am an Inspire person, they use the software for Inspire, but they could use the TI 84 emulator as well. Okay, so this is going to allow us to change the transmission numbers and the days contagious. And so I'm just going to leave them that way right now. It has my same population. Here's my 10% immune. Here's my 1 infected. Here's my 89 people who were susceptible. And this just sets everything up. This will do exactly what we just did, but it automates it. So at day 1, I have my first newly infected person infected 2 more, so I have 3. And so it's keeping track of everything. Day 2, I got 2 more people. So I keep looking, I watch the numbers. Vaccinated stays constant because that was my 10%. So I keep going. I'm going until I either run out of uninfected people or until I have no more contagious people. I have uninfected people. There's 0 people left to be infected. So notice there's no gray dots. So everybody in this entire population either was immune or got the disease. Some of them the pink ones are recovered. The black ones are still contagious. They have to go another day. When I go to day 8, those black ones should all start disappearing. Okay. And so I can continue to do that, and I can do it over and over and over again really quickly. Oh, I'll just actually go back here and show you this picture. And the picture is really kind of cool. Becky, if you do any calculus ever, you have to kind of change the axes, but it's kind of a cool thing to do for the calculus stuff. All right, I'm going to go back, and I'm going to actually try to get us into a different space. So I'm going to change this 1.2 to what we think, at least in the United States, is the transmission number for COVID. Yeah, and I'm not sure what it is, Leandro or Anna, I'm not sure what it is. I think PIP.1.2 is kind of okay for New Zealand. The days contagious, it varies. I'm going to go with 4.
In Brazil, the number was 1.
Was what?
1. 1 to 1.
1 to 1?
Yeah.
For the transmission number?
Yes, it's the high level that we have to stop everything.
Yeah.
Is that you asked?
Yep, that's it. Right. So when you get to 1, it'll balance out. I'm going to go with 1.2, and you can change it to whatever you want for Brazil or for New Zealand. And I'm going to go with 1,000 people here. So I'm going to have 100 of them. And then I'm going to have 899. And this is my population. So I have 1,000 people, stay with 10% immune. 1 newly infected person enters the community. And now I'm going to see what happens.
Okay.
And I can go back to, I start my slider over again. I can either count down or just start at 0. So here's all my gray people. This is all the people that are in my population who were standing from our original one. And the blue people are all the people that were initially immune because they were either vaccinated or because they got the disease already. And now I'm just going to see what happens. And you can see that it's taking longer for people to recover because the recovery period is 4 days. So far, I've only got 2 of those people recovered on day 5. So these are kinds of things that you want to worry about when you're looking at the capacity. When does the peak number of people who are ill? What's the hospital and the care capacity? I'm still going. I'm liking to see lots of pink because that means people are recovered. I need to go until the contagious is down to 0 or the infected is down to 0, the uninfected rather. Say 15. And when you do this on the handhelds, on the 84, I don't go much beyond a population 200 because it takes a long time. On the Inspire, you can go more, but you have to be a little careful. It always works faster on the software than it does on the handheld. So we can easily see that the disease worked itself out of the population in 21 days. What's the herd immunity threshold? Well, that would be all of the people who were vaccinated and contacted the disease, or 1,000 minus 41%. So that would be about what, an 80 something, 79%, 80%?
90.
I don't do my arithmetic well. So it's like,
what does it mean, the 41%?
So I need to know what percent of the population contacted the disease or was vaccinated. You're right, it's 95.
Yeah, 95. Where you got?
I don't either. Yeah, straighten you
Or
out.
someone ring the bell and the dogs start to bark and they lost what's
That's okay.
at the home it's happened.
Hey, Ken, what's up?
We're all used to that, right? I have a grandfather clock that chimes in the middle of lots of things. So, all right. So it's 95% herd immunity. Okay.
All right, I'll get you down sometime tomorrow.
All right.
Thank you.
About that. And I can reset this to day 0. Oh, no, I don't want to do that yet.
Yeah, Veterans Day.
I want to go over here and just look at all the data, and I can go here. It's kind of hard. I'm going to reset the window so you can actually see what the window looks like. And let me go do that out of state.
Yeah. Yeah, that's one.
I want to do menu, window, zoom data, because that's easier. And that's what it looks like. So you can follow the trajectory of both the recovered, the infected, and the susceptible to read off the herd immunity threshold. Okay, does that make sense?
Yes. I was wondering, in this simulation, you didn't not consider the people who died?
No. So that's another way to look at that. We did not do that. You can look at the people who died. You can also look at the percentage of people who get hospitalized. So there's a lot of things that get interrelated with this. For this take, we kept it pretty simple. We tried not to put too many conditions into the whole thing.
Well, and you could look at what percentage of the people I mean, they've got the known percentages of the people who are infected who end up being either hospitalized or who die.
And those are great questions that you can use in that following up part.
Yeah.
Yeah.
And the other problem, and the other reason that I think we get real complicated, Gail, is that those two things, whether you recover or hospitalized / die, is different on whether you were vaccinated to start with or not.
Right.
So that would make it even a little bit even more complicated.
Right. So I have a question. Do any of you, well, Becky, you probably do. I don't know if Kim and Lee, you probably do. Do you want to have an Inspire? Do you want to run this file yourself, or do you want me to show you?
I don't have a handheld. I've got and actually, I can run it on my my laptop.
Well, if you guys would run it on what I would really like you to do, if you have it, I want to actually investigate these questions right here. I want to know what happens if the number of uninfected or the vaccinated changes from 10% to 50% to 85%. So the only thing that would be different in your simulation would be running this exactly the way I've set it up. 1.2, 4. But we can control, that's what we're trying to do, is control the vaccinated. Now we can change the course of the transmission as well by masking and, stay-at-home orders and things like that. But we can also, and one of the things that they're trying really hard in the United States to do is to control the number that are vaccinated. Okay. So this was at 10%. So you would change it to, for 50%, you would make this 500. And then this would have to be 490. Oops, I forgot the zeros.
And Gail, we get it off of the website?
Right off the website.
All right, let me go on the website.
And so we still keep the same 1,000 people. We have 1 newly infected, and we have 499 susceptible people now, because half of our population has been vaccinated. So Leandro, what's it like in Brazil? How many, do you know what percent has been vaccinated? You're muted.
All right. I'm not sure, but I think about 70% of the population. We start to vaccinate the 12 years old people, teenagers. Yeah, so we finished the first, but I think we have the same problem in other causes. People are not believing that vaccination will be the solution.
Right. And so hopefully this simulation will help them see that. I don't know, Kim, where you're from. I know Lisa's from Minnesota, but the different states have different vaccination rates as well.
Oh, yeah.
And so that makes a really big difference. So if you guys could just, try that.
It's just, I'm just opening it right now. I just got the file ready to open. So if you go back to a page so I can see where I'm supposed to put what I'm supposed to put in 1 second.
Okay.
It's just opening. All right. What page are you on?
I'm on page 1.3.
1.3, and you want me to change transmission to 1.2?
Right. And be sure you hit enter or it won't give you the little green done stuff.
Right. And days contagious is 4. Got it.
All right.
Okay, next page.
And so why don't you do this one? I don't know, Becky, you could do 85%. So you'd have 850.
500, 500, 499. Got it.
Okay. Then you go over here, change the days to trigger it back to 0.
Okay.
And click away. I don't know, Kim, if you're doing that, or Lisa, if you're settled in from your kids or going back and forth or whatever, but.
Oh, I'm on page 5. I need to be on 1.6. Okay, here we go.
It still works on page 5 as well.
Oh, okay. And we want either, contagious to get down to 0, or
Yes, you want to get the contagious or the uninfected to get to 0.
okay, uninfected got to 0.
All right. So, Becky, are you on this at all?
I am sorry. Yep, I am. I'm at 0.
All right.
So I got that.
So I want to go to. So I want to go here to 2.2, and I'm going to enter your data. And so you guys are, you would, so what did I get for the 10%, the number of days? What did I get?
Was I 10%? No.
No, you were, come on. Why is this not doing what it's supposed to do here?
No, I was 1.2.
Oh, you were right. Okay. So I want to enter over here. You were 50%. How many days did it take you, Lee?
16.
16. And how many uninfected did you have?
At the end, 0.
And how many, what was your herd immunity threshold?
That's the contagious. So that's the which is it? The vax plus the immunity, so 95.
Okay. How about you, Becky?
It only took 6 days.
What?
I was at 85.
85, yeah.
It only took 6 days.
How many days?
6.
6.
Yep.
How many uninfected?
I had 298 uninfected. So that would be like about 70%, right? No.
Okay. And the herd immunity threshold?
Remind me what that was again.
That's
Vaccinated plus immune.
857. So
out of 1,000.
So 85.2.
85.8%. All right. So basically, I would have the kids do this for each group of kids, would do this over and over and over and over again, what you just did. And so to fill out the spreadsheet and plot it. And so I'm not going to do that here. I'm going to look at this, and I'm going to say, all right, here's where I actually carried it out a whole bunch of times. Alex helped me. So we did what you did for 10%, 50%, and 85%. And what would you think I would want to do next?
Compare the sampling distributions for each one of those.
I would think that's what I want to do. So I'm going to insert a data and stats, and I'm going to look at the days. And then, because Becky said compare, I'm going to add an X variable, and I'm going to look at the days for 50%. What do you notice?
It's not, though, 50% is way more variability. They're centered fairly close to the same, but there's a whole lot more variability.
Okay, and then I'm going to look at the days for 85%. We got a conjecture?
I'm trying to figure out why they would all be centered around the same place in my head, but I'm conjecturing they're going to have a similar center, but it's going to have less of a spread.
That's what I'd go with too.
There you go.
Huh. Nope.
No, it's not. It's a very different center. It's way down.
So it takes you many fewer days when you have a higher vaccinated rate. When you have 85%, your disease does not last. So it can last as long as 60 days. But for the most part, it's going to last between 5 and 10 days.
Really interesting is that 50 and that 10% though, like you said, it's got a mean that looks like they're, about the same. That's interesting.
Yeah.
Okay, you ready for the next one?
Yes.
Okay, so I'm going to insert data and stats. I'm going to add, let's add the herd immunity threshold. And then I'm going to add, that was the 10%. I want the 50%.
Interesting.
Why? What's going on with the
That's a very good question. What the heck's going on? Because that's bizarre.
With the 50 though, your bare minimum could only be a 50, whereas 10%.
Think about what happens with 50%. What could happen on the first go?
You don't infect anybody.
Right, because half my population has already been infected, right? So I'm not sure if I have this next here. I have it somewhere in here. There, whoops. I have it there. So in this simulation, nobody got infected for the first 4 days.
Because there were so many people that were immune.
Right.
Nice.
Right. And so this is what that looks like. It took 8 days for it to die out. It doesn't happen a lot, but it happens often enough to actually, and it can be explained away by, is this what the page we run? By what we were looking at. And I've kind of given it away now because I worked that out, but I'm going to add in the third variable, the 85% herd immunity threshold. And you shouldn't be surprised. So what does this mean now? (85) herd immunity threshold is about 85%.
Really and truly, nobody gets infected because there's nobody to infect. Very small population.
Right. So this is the answer to Leandro's question. It really is a way to think about why is having a large percentage of our people important to be vaccinated? Because if 85% of the population is vaccinated, it dies out in a quick hurry and hardly anybody else gets it. And so here, it can maybe not, or occasionally 50%, but for the most part, we have all these up to 98% for our here. That means 98% of the population. But remember, only 50% were vaccinated. So lots of people are getting it.
48% would get it.
As a matter of fact, let me just go to the next one here of all these ones that I tried. So Alex, who's a statistician, so he thinks really good about this stuff. He said, well, the thing we care about is what percent of the population is protected. And when you vaccinate 85% of your population, what percent is protected? Nearly 100% of your population is protected. When you only vaccinate 50%, what percent of the susceptible people now? So this one was divided by the susceptible, it was divided by the 250. This is divided by the 500. This is divided by the 900. So see, when you have just very few people vaccinated, hardly anybody is protected. When you have 50% of the people vaccinated, there's still lots of people who are not protected, who are susceptible. But when you get to the 85% level, you in only 1, 2, 3, 4, 5, probably six of the simulations did we get less than, and these are in the 95s, 95, 96% of the people are protected. So it's like, to me, this is the Tukey interocular impact.
So my question is, it's because we have a mutation of the virus, and the time, for example, if you vaccinate 50% of the population, we have more time to the virus spread, enter the people. So should have mutation, something like that. That is because not work. That's why not.
Yes, and so this is under the assumption that the days contagious is 4, and that the transmission rate is 1.2. The days contagious could change depending upon the mutation of the virus. So some mutations would change your days contagious, and that you can then run that simulation over again and collect the data and look at what happens if the days contagious increases. That's what you might want to do. But the idea here is basically to give kids a sense of what does herd immunity mean? Why is it important to increase the percent of people who get vaccinated? What's the impact likely to be on our population? Does this make sense?
Yes, it makes.
Does anybody have any questions? Anna had to leave us because she's teaching a class. Kim, do you have any questions? Lisa?
I got it downloaded and was playing with the numbers and just absorbing in what you say, thinking how to present it to my kids. Thank you.
Okay.
I lost where could I take the link to get the simulation?
You can
Google Math Inspired.
Yeah. Google Math Inspired Modeling.
I have it. Do you want me to just drop it in the chat box?
Oh, Becky, can you do that? That'd be awesome.
But it's nice to know how to Google it, because if you want to find some of the other activities in the future, that's because there's lots of good stuff on that site.
Yes, there is. There's another one. When we originally planned this workshop, we were going to do both the screening test results. What does false positive, false negative mean? How does the conditional probability play out? That's in there as well. And it didn't take Pip and I very long before we realized that wasn't going to work. That just doing the herd immunity was going to take care of our time.
And which one is the one you're talking about?
Examining medical test results.
All right, let me go back to the website.
Did you find it, Leandro?
Is it the one called? Well, there's rate. Let's see. There's
yes, it is.
Medical modeling. There's ratings, which has got modeling QB passage rates.
It's under simulations.
It's
under one of the simulations. Okay.
Yeah.
It's the one that's medical test results. Okay, I do have that. Got it. Thank you. Thank you.
Yeah. And these all the ones in this modeling are data driven. There's data sets that are underlying them, but and they are really fun. Let me tell you, we've had just a great time. You guys got to look at when you if you like cool things, you got to look at the flood one. Tom excelled in
which one?
The one that's modeling the flood. We got Hurricane Sandy hit the east coast of the United States really badly, and they had to figure out how to minimize the damage from the floods, and they used data and graphs and to do it. It's very cool. we have to leave our breakout room here pretty quick.
Data science are the two that I've not seen before. That's food truck and optimizing
Resources.
with census data. Okay, that's the one. Those are the two I haven't seen before.
Yeah, the food truck is fun too. They're all fun. But this one was designed to help us get out to the public what some of the underlying meanings of these words that they throw around. Okay. Are we all back mostly? Any comments you want to share in the chat or even orally before we kind of bring things together?
I mean, we sat in one session and got how that worked. Is it possible to get like a 5-minute overview of how the other one worked?
I
know that's tough.
I'll think.
So Lee, hopefully I've videoed my session if you went in my one, and we've definitely videoed Gail's. So we will make those both available. Yeah. But we can if
that would work. If I can just see the video of it, that would be excellent. Thank you.
And they will be on the IASE website. So you will be able to find them there.
Okay.
And you don't have to be a member of IASE, but we would love it if you were were a member.
We'll come back to that.
Yeah. Any other questions here? Oops. Before we move to close.
I just didn't get if the Inspire is free or we'll have to pay.
Inspire is you can get a free download of Inspire. So it's a trial version. It lasts for software. It lasts for 90 days. You can probably fudge. And once your 90 days is up, you can wait a while and then do it again. And that will.
That though, you have to completely strip it off your machine. It will detect that you have to strip it before it expires. So about day 85, you got to get rid of it. I'm serious.
Experience.
I want to ask one question for this. Is it okay for KCU models? Because I have CG50, this one. I have CG50. I think this also can handle simulations.
I am not familiar with that, but I'm sure, knowing Casio and the functionality, that you would maybe not be able to do what we did in the breakout sessions. I know you could do what we did before the breakout sessions on your Casio.
Okay. Okay.
Yeah. Other questions? Before I kind of wrap this up, I wanted to just remind us about the process, because I think that's really important. There's always a tension of getting to the stuff where you can click the buttons really fast and see how the powerful stuff works. But I really think starting with the people and their hands, or standing up, sitting down, is an important part. So these pieces are all part of the process. And I think there's something that we shouldn't let go of, that we should be sure that we keep in the forefront of this. And in the activity that we actually worked on, that you have an extension where you can actually look at other kinds of diseases and apply the same software, the same techniques to think about what's going on with other diseases or in other kinds of instances. So before I turn this over to
Gail, can I say one thought?
Yes.
Love the idea of doing it manually. I almost think it'd be better to do it totally manually, like the spreadsheet that Pip was sharing, rather than try and showing you how would do it, how Inspire would do it, but do it, And
No, you're right. You're right, Lee. That's how you would do it. You finish it totally manually. You don't stop in the middle. Yeah. You're right.
Totally manually. You don't even use the Inspire at all, and then go and here's a simulation that will do the same thing.
Yeah.
I mean, I think trying to show them building the steps of how you got the Inspire to do it is not worth the time it would take for them to understand. Does that make sense?
It does. It's worth thinking about. All right. So here's the page where the activity itself and the directions would work for whatever software you're using. The activity would be there. So I wanted Alex just to say a few minutes. Alex has worked on some of this modeling stuff. So Alex, can you just say a few things about what we just did and why it's important? Putting you on the spot.
Yes, so a couple of things is one, that there are network models of spreading disease that they use that use exactly the kind of simulations that we were using right here in order to model who you have exposure to, because the mathematical or differential equations kinds of models that people are usually referring to, even in the media, those sort of assume that everybody is exposed to everybody. And the other thing is that the variation in the models is very important, and there's quite a bit of variation between the different kinds of models that people are using to try to predict the spread of the disease, depending on what assumptions they make. But also they assume that there's a lot of randomness involved. And so the modelers are very careful not to say, this is the number that we're talking about, but they try to give a range of numbers. So I think it's important that we learn and we teach our students to expect that kind of variation and try to figure out how we can make decisions in a context where there's lots of that kind of variation. And I know that when they work with policymakers like health professionals and governors and et cetera, they have a hard time communicating that lack of certainty in their numbers.
Which is why we think something like this, it'd be really valuable for kids so that when they get in that position, they understand something about that uncertainty and to expect uncertainty as part of the deal. And the SRI model, susceptible, infected, recovered, is actually at the end of the TI Inspire. You can actually go through the file. It's actually there. That's the theoretical model, comes out of differential calculus, I think. But again, we put that towards the very end of it. So here, there's a Jamboard. Monica or somebody, can you put that in the chat so that people could share any thoughts on their Jamboard?
Done.
Great. You guys are so awesome. This has been a wonderful team to work with. I want to say thank you to Aisha and the IASE Executive Committee for letting us do this, and for Pip for all of her work and thoughts, and to Alex and Monica for helping us make sense out of this. I hope you guys had a good time doing things in Spanish as well as English. This was our first go for that, and hopefully we can make something like that happen again. So Pip, I think this is my parting shot about ISI's role to support us, to empowering our students who can become empowered citizens. I think this is pretty important. And Pip, this is you.
Okay, so in the links, I've put the link to the membership page. So we would love it if anybody wanted to join us. And teachers, there's quite a reduced rate for teachers compared to researchers and those of us working in institutions, but there is a lot of stuff that you get from being an IASE member. And did I put another page, or did I just give you one page, Gail? Did I put one about the webinars coming up? What's coming up? Okay, so just a couple of other things that are coming up. So the Paderborn Colloquium, there's a link there. which is on the website, the IASE website. That's coming. There's 2 more sessions, and I got up at 3 o'clock in the morning the other day for one of those, and it was great. And then we've got ICOT, so Teresita's here, and the abstracts for that are due on the 17th of December, and Teresita's the local organising chair, and there's the website there if you want to go to ICOTS. Now, ICOTS is hybrid, so if you've not been able to travel before, you might find it an opportunity that you can go because it's hybrid. And the IASE webinars, I put the link also in the chat. We do have a page now. It's only just new. And on the page will be soon, I'm not promising in the next 24 hours, but soon will be the recording of the webinar and anything we can share with you, links, the PowerPoints. Alex has done the PowerPoint in Spanish as well. So we'll put all of that up there for you. And when it is up there, I'll send an email to tell you that it's up there. All right. So if you're registered, I've got your email. And then when we know about the other webinar, I will send you an email as well with the information about the webinar. And I will keep you on my webinar list until you tell me you don't want to be on it. So even if you're not an IASE member, you'll be on my webinar list. But we do hope you'll join, and we do hope to see you at ones in the future. And if you just want to give any feedback at all to Gail about the session or to us about the session, we'd really welcome that in the chat. And we look forward to seeing you all at the next one.
Thanks, everybody.